Good afternoon, everybody. Welcome to today's live stream on acids, bases, and pH. So I'll put the link to the notes in the description, and hopefully you've had a chance to print it out because we're going to go through them any second now. Yep, there's still a live stream today. This is it. But I am technically on holiday now, so it feels a bit weird to be doing this, but there you go. All right. Right, okay then, so the topic acids, bases and pH, remember I teach OCRA, but it doesn't really matter which exam board you do, it's all pretty much the same stuff. So the way OCR organises the course is there's this topic here, which is called acids, bases and pH, and then the next topic is called buffers and neutralisation. So you'll notice that if you've had a chance to look through the notes, you'll notice that buffers aren't in this pack of notes. They're at the beginning of the next pack of notes. So it makes sense to do buffers and neutralisation after this one. The very, very last calculation in this pack of notes is actually very, very similar to the first type of calculation in the next set of notes. So there's kind of a nice kind of crossover between the two topics. Okay, but technically buffers is not until the next topic. I hope that all makes sense. Okay, so without further ado, shall we get started? And hopefully we'll get through a decent amount in the hour. I'll keep an eye on the chat and try and answer the sort of questions as they come up, but remember there is a bit of a delay, so it's not the easiest thing in the world. Okay, here we go then. So acids, bases and pH. So the first thing we'll do is we need to define what's called a Bronsted-Lowry acid and base. Okay, so there's various definitions for acids and bases. So you can have a Lewis acid and base, for example, but Bronsted-Lowry is the definition that's used at A level. Okay, and that's just the surnames of two chemists basically. Okay, so a Bronsted-Lowry acid is defined as a proton or an H plus donor, and a Bronsted-Lowry base is the chemical opposite of that. So if an acid's a proton donor, a base is a proton acceptor. Okay, and obviously proton H plus, you can interchange those. Right, so I've got three examples of acids. I'm writing them all as reversible processes. There's kind of a point to this. So hold the questions. So you might be thinking, hang on a minute, why are you doing it that way? But hopefully it'll make sense when I get to the end of this little section. So hydrochloric acid, when that's in solution, it dissociates into H plus ions and chloride ions, of course. And you'll notice here I've got a Kc, the Kc code from equilibrium. Remember, that's a measure of the extent of the equilibrium position. And so because this acid is very, very highly dissociated, Kc for this acid is very, very large. I'm not going to quantify it, I'm just going to say that it's very, very large. Okay, so this equilibrium is very, very much that way. Okay, the next one, nitric acid, dissociates into ions. So we have H plus AQ and the nitrate ion NO3 minus AQ. And Kc for that is also very, very large. So I'll draw a big arrow like that. Okay. The final acid, ethanoic acid, that will also dissociate and donate an H plus ion, otherwise it wouldn't be an acid. So into H plus AQ and CH3, COO minus AQ. And the Kc for that is very small. Okay, So this equilibrium is going to be that way. Okay, so you're going to have far more of the undissociated CH3COOH compared to the H plus and CH3COO minus ions. Okay, so the point of doing that is to try and establish the difference between the first two acids that have these very large Kc values and the third acid, which has a very small Kc value. Basically, this is telling us the acid strength. So HCl and HNO3, so hydrochloric acid and nitric acid, are what we call strong acids. Okay, i.e. they are fully dissociated. Okay, so really, I'm going to amend these notes now. What we do, instead of having the reversible arrows, we use a single arrow there. Okay, a one directional arrow. Likewise, we do the same for nitric acid, which is also a strong acid. So we use that type of arrow rather than the reversible arrows. Whereas for ethanoic acid, which is a weak acid, I'll write that up in a second, we use the reversible arrows, okay, because it's only partially dissociated. CH3COOH is a weak acid, i.e. partially dissociated. Okay, so I hope the use of the reversible arrows at first there made sense. Okay, and obviously I've gone back and changed it to the actual arrow that we use. Okay, so very quickly we've established what an acid is, a Bronsted-Lowry acid, what a Bronsted-Lowry base is, and the difference between a strong acid and a weak acid. And it's all about the extent of dissociation. Okay. Right, so the next little thing here is we're going to establish, or we're going to introduce this term conjugate acid-base pairs. So the first thing I'm going to say is the equations above are all simplified. So those three equations for the hydrochloric, the nitric and the ethanoic acid, they're all simplified equations. There's nothing wrong with them, but they've actually been simplified. And that's because acids need a base to donate the H plus 2. Okay, so basically, as those equations are written at the moment, it just looks like the hydrochloric acid is throwing the H plus away. Okay, and it's not really going, it's just going on the other side of the arrow, if that kind of makes sense. What's missing from this side of the equation is the base that accepts the H plus ion. Okay, so I've gone for the second equation here. So I'm going to do the second equation, the nitric acid one, more fully. So remember, HNO3 is an acid. Okay, so it's going to donate its H plus just like it does in the simplified equation above. But what it's going to do is going to give it to the water, okay, because there's water present, obviously, because it's all in aqueous conditions. So the water is actually going to accept that H plus ion. So what's going to happen is the water is going to become an H3O, so it's just picked up the H plus, but obviously it's going to pick up the charge as well. So it becomes this H3O plus ion, okay? And what's left is obviously the aqueous nitrate ion. Okay? So that's the full way of writing the example 2 equation. Okay, so we've got the simplified version here, which is absolutely fine, but it doesn't show where the H plus is actually going, whereas this one does. So I hope that kind of makes sense. So what we're going to do is we're going to work out what the conjugate acid-base pairs are in that equilibrium. Okay, so let's just have a look. So this is definitely an acid because it's donated a proton. So we'll call this acid 1. Okay, now the water is a base. We've established that because it accepts a proton. Okay, but it belongs to a different pair. So we're going to call this base of pair 2. Okay, so we've essentially got two pairs of things. Each pair has an acid and a base. Okay, so let's just have a look at this again. So the nitric acid is obviously an acid. So we'll call this the acid of pair 1. So basically, what's the other part of pair 1? It's going to be a base, okay? And it's this thing here. So this is the base of pair 1. So I'll just explain why that's a base, because if you think about this reaction in reverse, what can this nitrate ion do? It can accept a proton and turn back into that. So these are linked by the proton, okay? So when that loses its proton or donates its proton, is probably the best way to say it. When that donates a proton, it becomes that. When that accepts a proton, it becomes that. So they are both pair 1s. They belong to the same pair, okay? This is an acid because it donates a proton. This is a base because it accepts a proton. I know when this is first, when I first do this in class, you can see a few sort of confused faces in the room. I hope this is not too confusing. It actually gets easier the more examples you look at, and that's why on the next page I've got lots of examples we can try. Okay, we'll just finish this bit off. So we've established this as a base because it's accepting a proton from the HNO3. That's what it becomes. So you can see that this can donate the proton, okay, and turn back into the water. Okay, so they're linked together as well. So that's the other pair, but this is the acid of pair 2. Okay, so there's a few things we can say here. So some little rules of thumb, and I'll say this again on the next page. On each side of the equilibrium, when you're asked to do these, you've got to have an acid and a base on each side. So you'll see we've got an acid and a base, an acid and a base. So that's one rule. And you've got to have a member of each pair on each side. So if you've got acid 1, the other thing has to be base 2, because you can't have two 1s on the same side. You can't have two 2s on the same side. You can't have two acids on the same side. You can't have two bases on the same side. I'm very tempted to say, is this making sense? Because I feel I'm just talking into thin air here. I know I'm not, because I know there are 9 people here, which is great. But I hope this is making sense. Probably make more sense when we look at the next thing. Okay. The final thing just to say on this slide is the special name for this H3O plus ion is the hydronium ion. That's just there for your interest. You won't be asked that. It's often simplified to H plus AQ. So the aqueous H plus ion is actually this thing here. Okay, that's the same thing. So the definition for a conjugate acid-base pair is a pair of species in an acid-base equilibrium, which is what we've got, that can be interconverted, so changed from one another, by a transfer of a proton. Oh, excellent, it made sense. Thank you very much for that. Okay, so that's the definition for conjugate acid-base pair. A pair of species in an acid-base equilibrium that can be interconverted by proton transfer. Okay, so what we'll do, we'll just make sure that's totally made sense with this exercise here. So I've just taken these from a set of questions. Okay, so we've got 5 things here, and what we've got to do in each one is we've got to identify the acid-base pairs. I'm just going to use sort of A1s and B1s and B2s and things for this, if that's all right. Okay, so let's have a look. Let's just pick up this HCl. What's it doing? It's becoming that. So you can see that, to go to that, has got to donate the proton. So this must be an acid. So we'll make that A1. Actually, I'll put the 1 there. So this must be the conjugate base. So that's B1. And then just think the definition. Pair of species in an acid-base equilibrium that can be interconverted by proton transfer. So that loses a proton, it becomes that. That gains a proton, it becomes that. Okay, so that's a pair. So let's adopt that little sort of rule of thumb. If we've already established the acid, that must be the base. It can't be 1, it's got to be a 2, because you can't have 2 1s on the same side. So that's a different pair. And obviously this is the acid of that pair. Okay? And just apply the definition. So are they linked by a proton? Yes, they are, because if you add an H plus to that, you get that. If you lose an H plus from that, you get that. Okay? I won't go through all of them as thoroughly as this, otherwise we'll be here all day. Okay? Right, so let's have a look at the water. So what's H2O becoming? H2O is turning into OH minus, so it's donated a proton. It's obviously gone to that. So this is A1. This is B1. So this must be B2. This must be A2. Okay. Okay, so the next one is a little bit more sort of obscure in the sense that these are both acids. Okay, so we are familiar with hydrochloric acid. Obviously there's acid in the name, it's an acid. And ammonia, hopefully you do know that that's a base. Anyway, okay. I suppose water is a little bit unusual there because it you don't really refer to water as an acid or a base, but you can see its role in that. These are definitely 2 acids, nitric acid, sulfuric acid. So maybe this one, Sadiqa, is what you're talking about. Let me know if you think it's anything like what you're thinking about. Right, so nitric acid, let's look at this first. So HNO3, and you can see it's become H2NO3+. So what's happening there is it's picking up a proton and turning it into that. So this is accepting a proton and becoming that. So this must be a base. We'll call it pair 1. It's the first thing we've looked at. So this is the acid of pair 1. Okay? So this is accepting a proton to base, turns into that. That can donate a proton and go back to that. So that works. So the H2SO4 must be acting as an acid, because you can't have 2 bases on the same side. So this is an acid, different pair, so 2. And when that donates the proton to the HNO3, it becomes HSO4 minus. So this must be the base of pair 2, B2. Okay? So kind of questions that they could throw at you from that is, what is that telling you about nitric acid and sulfuric acid? That tells us that sulfuric acid must be a stronger acid than nitric because it's the one that donates its proton. Okay, so we'll just put a little there for H2SO4, stronger acid than HNO3. Okay, because it's the one that's donating the proton. So if we look at the next pair, so we've got H2O and HCl. What's H2O becoming? It's becoming H3O+. So it's accepting a proton from the HCl. So this is a base. So we'll call that B1. So this is A1. The HCl is donating a proton, so that's an acid, different pair, so A2, so that must be B2. Okay, and then the final one, again we've got two acids present. We've got methanoic acid and nitric acid. So let's have a look at the methanoic acid. What's it turning into? It's turned into this. So you can see the difference is a proton because it's got an extra H and it's got a positive charge. So this must be a base. So it's accepting a proton. So we'll say B1. This must be A1. And therefore the nitric acid is A2, B2. Okay. And I'm just going to make them red. Don't know why, but I'm going to. So this was A2, B2. So how are we feeling after that? I hope that still makes sense after seeing all those examples. So I think what I try and reassure my students is if you can just remember you need, I've said this a few times now, an A and a B must be on each side and a 1 and a 2 must be on each side, and it's quite easy if you sort of adopt that. Okay, I'll move on, and then obviously if somebody puts a question in the chat about that, I can always go back to it. Okay. Right, so the next little thing is about types or classifications of acids. So we've already had the strong-weak classification, and that's about the amount of dissociation. We've got, makes sense more, brilliant, thanks Laura. We've got different types of acids, so we've got monobasic, dibasic, and tribasic, okay? And this is all to do with the number of protons or H plus ions that are replaced in the acid-base reaction. Or you could think of it like how many protons does it donate, okay? So hydrochloric acid, formula is just meant to go in there. And you can see straight away from the formula, that's only got one proton to replace. And so this is what we call a monobasic acid. Mono obviously meaning one, monobasic. Okay. Ethanoic acid, CH3COOH. So sometimes as a teacher, I see some students thinking, all right, it's got 3 hydrogens there and another one there, it's got 4 hydrogens. And they might say, what do you call an acid that can donate 4? Well, it can't donate 4. That's the proton that it donates. So there's only one of those. So monobasic again. Okay. So all carboxylic acids essentially are monobasic, or all the simple ones like that. Okay. Carbonic acid, so if I give you the formula for that, is H2CO3. So you can see it's got 2 sort of replaceable H pluses, these 2 here. May as well highlight that as well. So this is dibasic. Okay. Let's highlight the H as well. And boric acid, you're not expected to know certainly the boric acid formula. Certainly carbonic acid comes up in a couple of things, so it's probably worth knowing that one. Boric acid, you wouldn't be expected to remember this, so I like to use obscure examples where I can, instead of the obvious stuff. H3BO3 is the formula, so it's got these 3 protons that can be replaced. So this is an example of a tribasic acid. Okay, so that's hopefully that's fairly straightforward. So if we I can just throw a couple of more examples at you. So another example, things that you're more familiar with, H2SO4 is dibasic, HNO3 is obviously monobasic, and phosphoric acid, H3PO4, is tribasic. They're the classic ones. I've avoided using those in the examples just to give you lots of different ways of looking at it. Okay. Right. So again, I'll do what I said before. So any questions, I can go back to that if you're not sure. But we're just going to keep going if that's all right, because I really want to start getting. I think it's the calculations that people will be maybe more interested in looking at rather than this sort of stuff here. Okay. Right, so this page here on the notes is called the role of the H plus ion in the reactions of acids. Okay, so if you think about it, I think about the H plus ion as like the active species in an acid. Okay, it's just my way of thinking about it. Active species. And you can see that from ionic equations that we're going to have a go at writing that. How would you find out? Right, that example there is, let me just think about that. That's not an acid-base equilibrium. That's an acid-base, like a neutralization reaction. I'll have to, off the top of my head, I'm not sure whether that would be classifiable, because obviously you've got the NaCl doesn't have any reference to a proton at all. Is that a question that you've been asked? All right, okay. How would you take this into account in titration questions? Well, the type of acid enables you to balance the acid-base reaction. So, for example, if you were reacting H3BO3 with, say, sodium hydroxide, you would need 3 moles of sodium hydroxide because there's 3 replaceable H pluses in the acid. If you react in carbonic acid with sodium hydroxide, you would need 2 moles of sodium hydroxide because of the 2 replaceable H plus ions. Do we need to know diprotic and monoprotic acids? Yes, you do. Well, for OCR you do, yeah, definitely. Definitely. I'm gonna do some research. I'm not dodging the question, but I'm gonna do some research into that HCl NaOH question, because I'm off the top of my head, I don't think that's an example of one of these, but I could be wrong, but we'll see. All right, I'll mention that next lesson, okay? So I can answer that for you next time, if that's okay. Right. The role of H plus ions in the reactions of acids. So this is a bit of revision really from first year. So acids react with, we know that they react with metals, they react with carbonates, they react with metal oxides, and alkalis, which are metal hydroxides, soluble bases, to form salts. Okay, so basically this is, great, thanks. This is going to be just a big sort of set of revision for all the different reactions that you need to know about for acids. Okay, right, so we'll go through this fairly quickly. I'm hoping that there's not going to be anything new here, and I don't want to leave it blank either. So let's just crack on with this. So the full equation, we need the state symbols for this because we're going to turn it into an ionic equation. So zinc is obviously a solid. we need to react that with 2 moles of HCl. These are aqueous. And we're going to get the salt zinc chloride, ZnCl2, that would be aqueous. And you get hydrogen, H2, it's obviously gas. Okay, so the ionic equation, all you do, I've just done a video actually on ionic equations, like a revision video. Basically, if the state symbol is aqueous, you need to split it into its ions. If it's a solid, liquid or a gas, you leave it alone. Okay, so you've got 2 aqueous species in there. I'll do this one in full and then I won't bother with the rest. Okay, so zinc's a solid, so it stays as it is. So this is 2 moles of H plus ions and 2 moles of Cl minus ions, because obviously that 2, that coefficient there, doubles everything, so it's 2 H's and 2 Cl's, so 2H plus, 2 Cl minus. That goes to a zinc 2 plus ion, which is obviously aqueous, and 2 chloride ions, aqueous, and hydrogen gas. Okay, that the 2 chloride ions because the little number 2 there after the Cl. Okay, so when we get to that part, we need to look for spectator ions, so they are ions that are present on both sides of the arrow, and you can see the chloride ions cancel out, and what you're left with is the ionic equation. Okay, so you would write Zn solid plus 2H plus aqueous goes to Zn2 plus aqueous and H2 gas. So the reaction type, that's not a neutralization reaction, that's a redox reaction. Okay, redox. So I'll just explain why. We've got the easiest way to look at it here is in the ionic equation. So zinc's an element, all elements have an oxidation state of 0, and it's gone to the Zn2 plus ion, so it's got a plus 2 oxidation state, and so therefore zinc has been oxidized, Zn oxidized from 0 to plus 2. The hydrogen has gone from plus 1 in the H plus ion down to 0. So that's a reduction process because the oxidation number has gone down. So hydrogen H is reduced. Okay, so that's why that's a redox reaction. Okay, next one is aqueous sodium carbonate and sulfuric acid. So the full equation first, so that's Na2CO3 AQ plus H2SO4 AQ goes to sodium sulfate, Na2SO4 AQ. So acid plus carbonate gives salt, water and carbon dioxide, so we need CO2 gas and H2O liquid. Okay, so we've got aqueous, aqueous, aqueous. So in terms of ions, we've got 2 aqueous sodium ions, 2 aqueous sodium ions, so they're going to cancel. We've got an aqueous sulfate ion and an aqueous sulfate ion, so they're going to cancel. So what we're left with would be a carbonate ion, CO3 minus AQ, 2 H plus ions, AQ, goes to carbon dioxide, gas, and water. So that's a neutralization reaction. It's not redox, it's neutralization. Okay, next one. Solid calcium oxide, so that's CaO, solid, plus nitric acid, we'll balance it as we go, so it's 2HNO3 AQ. All of these salts formed in neutralization would always be aqueous. Acids, alkalis are all aqueous. They normally would say in that there would be a hint to whether it's aqueous or not in the question. Calcium oxide plus 2HNO3 goes to calcium nitrate, that's CaNO3 twice, AQ and H2O liquid. So let's highlight the things we're going to have to turn into ions. So what have we got here? We've got 2H plus ions and 2 nitrate ions. We've got a calcium 2 plus aqueous ion and 2 nitrate ions. So the 2 nitrate ions are going to cancel. So we get I scribbled there. CaO solid plus 2H plus aqueous goes to Ca2 plus aqueous and H2O liquid. Okay, and then the final one, sorry, that's neutralization as well. Aqueous potassium hydroxide and ethanoic acid. So notice it says aqueous there, so that's helping massively, isn't it? Ethanoic acid will be aqueous, the acids are aqueous. So it's KOH AQ plus CH3COOH AQ goes to, you'd get the salt potassium ethanoate, so it's CH3COOK AQ, H2O liquid. Highlight the aqueous species, okay, and think about what's going to cancel. So we've got a K plus aqueous and OH minus aqueous, CH3CO minus aqueous and H plus aqueous, CH3CO minus aqueous, K plus aqueous, and H2O liquid. So what you're left with is simply the hydroxide ion, the H plus ion, go into water. So that is the classic neutralization ionic equation. Okay. So the reason why that part of the notes has the title at the top there, the role of H plus ions in the reactions of acids, you can see from the ionic equation that it is the H plus ion that's actually reacting, being involved in all of those reactions, and that's why I call it the active species. Why do you include the other molecules in the ionic equation? You only show the ions if the thing is made from ions. So water is not made from ions, it's made from H2O molecules. So you only show ions if it's basically if it's aqueous, because all aqueous substances will exist as ions. How did I know that potassium ethanoate formed? From my, well, this is the trouble now, isn't it? Because when I teach acids and bases in first year, I would always use equations that I know are going to be helpful for second year. So I would use examples of neutralization reactions involving carboxylic acids and things like that. So just going back to clutter-free, can I suggest that you watch my videos on ionic equations? Because obviously there's a lot more detail in those. So, you know, hopefully watch that. They're only 5 minutes long or something like that. And hopefully by the end of that, it'll make more sense. And then these notes will make more sense. Okay. I'm basically trying to sort of shoehorn, you know, 2 lessons into like an hour with these notes. Okay. I wouldn't go through things this quickly normally. In college I would be doing lots of little exercises and things like that. So, you know, it's kind of, it's probably going to be quite difficult to take everything on board first, you know, at the first listen. Okay. Right. So we're moving into a sort of different realm now of the topic. We're going into the sort of calculation aspects of things. So this is where, if you use a phone for your calculator, which some of my students do, I'm sure most students use their phone calculator. I would definitely discourage that and use a proper scientific calculator, especially for stuff like this that's coming up now. Okay, right. So pH, I'm sure you've all heard of pH. So just some basics first. Solutions with pH numbers less than 7, but I'm going to stress that's only relevant if it's 25 degrees C. You'll see why when we get on to something called Kw, okay, which is called the ionic product of water. So the temperature has to be 25 degrees C for these statements to be true, okay? So solutions with pH numbers less than 7, but it has to be at 25 degrees C, are classed as acidic. Sorry, I don't like the red. Solutions with pH numbers greater than 7, but it has to be at 25 degrees C, are classed as alkaline. And solutions with a pH number of 7, but that's only true at 25 degrees C, are classed as neutral. Okay. Okay, a couple of definitions. pH, so don't be saying things like it's a scale, it's a number scale that goes from 1 to 14 and it tells you how strong an acid or an alkali something is. The definition for pH is the negative log. You can put a little 10 there if you want to, or I don't bother normally because log is so for that one there, I always tell the students which, I think we've had a little bit of issue there with connection, probably on my part, I'm afraid. Sorry about that. I think we're okay now. So H plus concentration is 10 to the minus pH. So basically on your calculator, shift log, and then the second thing you do is type in the minus pH value. Okay. Right, so some practice now. If you've got your calculators there, you can sort of do these as we go. But basically, which part do you mean? Do you mean the pH part or the H plus concentration part? Both, okay. So the definition of pH is minus log of the hydrogen ion concentration. So if you're asked to define pH, you write that formula down. Okay, you literally write the formula down. These won't be given on a data sheet, I'm afraid. You've just got to learn them. And if you're wanting to do the opposite of that, so if you're given the pH and you want to calculate the H plus concentration, the hydrogen ion concentration, it's 10 to the minus pH. Okay. So the first set of the first exercise is you've got the H plus concentration, and we're going to calculate the pH to 2 decimal places. So we're going to use this formula here, minus log H plus concentration. So I don't know if you want to have a go at those, and I'll give you, how long shall I give you? A minute, 2 minutes to try and do those. So it's literally just minus log and then type in the H plus concentration. Okay, minus log and then that number. Okay, and see what you get. Okay. Apologies if that wasn't enough time for you to do this. So I got for these, and these are the answers by the way. So the first one is 1.60. This one is 0.60. We've got 2.61. The next one is deliberately sort of included there just to make people aware that you can have negative pH, just very, very strong acid this. So that's negative 0.22 would be the pH to that. And the final one is 7.43. Okay. I don't know if it's in GCSE, sorry, I don't teach GCSE. I would be very surprised if it was, but I mean, somebody could correct me. I'd be very impressed if, you know, year 11 students were dealing with this sort of maths. But, could be wrong. Okay, the next ones are where you're given the pH and you've got to calculate the H plus concentration, again to 2 decimal places. So the order that you press your buttons, shift log, and then type in the negative of the pH. So it'll be shift log minus 5. Okay, shift log minus 4. OCR don't. You can do pOH calculations. That's just the minus log of the OH minus concentration, but that's not something on the OCR syllabus. But you can use it to calculate the pH of a strong base, which I'm assuming you're Richard. Okay, Richard, me 1, 2, 3. Okay. So basically anything with a P in front is minus log. Okay. What they could do is they could sort of give you some information about what pOH means and then get you to do some work on that. But they've then told you what it means, if that makes sense. So they do that sometimes, where they'll throw something completely new at you, and but they will explain kind of what it means, and then expect you to work with that. Okay. Right, I'm just going to go through these then. So if the pH is 5, the hydrogen ion concentration is 1.00 times 10 to the minus 5 moles per decimeter cubed. Yep. Next one would be 1.00 times 10 to the minus 4. The next one is 1.48 times 10 to the minus 3. The next one is 1.62, and the final one is 4.27 times 10 to the minus 13. So I hope you got all of those correct. I'm sure you did. Now, the reason why I use some of these numbers is because, well, certainly these two here. Okay, so you can see here that this is a difference in pH of 1 unit, isn't it? pH 5, pH 4. Okay, so that's the stronger acid, isn't it? The lower the pH number, the stronger the acid. So pH 4 has a hydrogen ion concentration of that. pH 5 has a hydrogen ion concentration of that. So hopefully you can see the link. The difference of 1 pH unit is a 10-fold difference in concentration of H+. Okay? Difference of 1, 10-fold difference, because you're going 10 to the minus 5 to 10 to the minus 4. Okay? And that's because it's all based on this log 10 scale. Likewise, I don't know if you noticed, but here I've got these H+ concentrations differ by a factor of 10. So this one here, 2.5 times 10 to the minus 1, is 10 times more concentrated than 2.5 times 10 to the minus 2. And look at the difference in their pH values. The difference is 1. Okay, so you've got that 10-fold difference in concentration of H+. You've got a difference of 1 in the number. Okay, so you can see how many times more concentrated an acid is from the pH difference. I'll explain that now. So since the pH scale is based on a logarithmic scale, a change of 1 pH number is equal to a 10 times difference in H+ concentration. So if you were wanting to dilute a solution from pH 1 to 2, you would dilute it 10 times. Okay? If you wanted to dilute from pH 3 to 6, so you're changing pH units by 3, aren't you? You're going from 3 to 4, 4 to 5, 5 to 6. You're actually, that's 1,000 times in terms of dilution. Okay? Because you've gone through 3 pH units. Each pH change of 1 is a 10-fold increase or decrease depending on which way you go. Okay? So hopefully that, I know when I mention that to some of my students, they actually sort of think, oh, that actually makes a lot of sense and quite interesting. Not all, but some do. Right, great. We've got into actual calculation of some pH of strong acids now, and I think, yeah, we'll try and do this page and half of the next page, and then that's probably a good place to stop, because then we're going to get to weak acids, which is different again. Okay, so since strong acids fully dissociate, so we're going back to the very beginning of the lesson, fully dissociate, the H+ concentration, which is what we need to calculate a pH, we need to know the H+ concentration so we can minus log. We can easily obtain the H+ concentration from the concentration of the acid, because it's fully dissociated. Once the H+ aqueous is known, pH can be calculated. Right, so let's just explain all of that. So if we've got nitric acid, HNO3, we'll just do the simple dissociation. That dissociates fully, remember, to strong acid into its ion, so H+ and NO3 minus. So if the concentration of the acid is 1.27 times 10 to the minus 3, look at the mole ratio, it's 1 to 1, so if you've got that many moles of that, it's going to generate the same number of moles of H+, and because that's in the same volume, it's the concentration as well. So 1.27 times 10 to the minus 3 is the concentration of the H+ ion. So that's why it's really easy to calculate the pH of a strong acid, because if you know the concentration of the acid, you therefore know the concentration of the H+ ion. So pH is just the minus log of 1.27 times 10 to the minus 3 into 2 decimal places, that's 2.90. Okay. Next one. If you've got, look, I've chosen the same concentration of sulfuric acid this time. So remember, H2SO4. So nitric acid's monoprotic, yeah. Yeah, that's right. Whereas sulfuric acid is diprotic or dibasic. So the dibasic and diprotic's the same thing, just two ways of saying the same thing. That's going to generate 2H plus and a sulfate ion. Okay, so if the concentration of the acid is 1.27 times 10 to the minus 3, the H plus concentration will be double that. I hope everybody can see why. It's down to the mole ratio. So that would be 2.54 times 10 to the minus 3. Okay, because of the mole ratio. So pH of the sulfuric acid is going to be minus log of 2.54 times 10 to the minus 3, which is 2.60. Okay, so you can see that these have got the same concentration, but you'll see the pH, look, of the sulfuric acid is actually lower, so it's a stronger acid. Okay, right. So save the best till last, or the hardest stuff till last. Hopefully this will be okay. Right, so this bit here is all about calculating the pH of a strong acid. pH doesn't have a unit, no. These are strong acids after dilution. Okay, so we've got to calculate the pH of the solution formed when 100 cm cubed of water is added to 50 cm cubed of 0.1 mole per decimeter cubed nitric acid. The scale, I think the problem with the scale is we're taught from a very early age that the pH scale goes from 1 to 14. It can go beyond that, and it can go into the negative if the H plus concentration is high enough. Right. Okay, so how we're going to do this. I like to use little pictures actually. So let's just imagine you've got so that's 50 cm cubed of 0.1 moles per decimeter cubed nitric acid. Okay, and then what's happened is they're adding to that 100 cm cubed of water. Okay, so obviously that's going to be, that beaker is going to be a bit more full, isn't it? Let's put it up to there. Okay, so the way I would think about this is, so we've got to calculate the pH of this solution here. Okay, remember what we need to know is the H plus concentration. H plus concentration, so we can minus log. So the first thing we can do, if we know the concentration and volume of this nitric acid, we can work out the moles of the H plus ion. Okay, I'll do this in black so it sort of stands out from the blue. So the moles of H plus from 50 cm cubed of HNO3 is going to be concentration times volume, 0.1 times 0.05, 5 times 10 to the minus 3. Okay, so that's how many moles of H plus we've got. I'll just put concentration and volume there so you know where that's come from. Okay, so there are, let's just put that in black in that beaker, so there are 5 times 10 to the minus 3 moles of H plus in that beaker. Okay, and then the 100 cm cubed of water is added. There's still 5 times 10 to the minus 3 moles of H plus in there. Just adding water isn't going to change the moles of H plus, is it? Okay, so 5 times 10 to the minus 3 moles of H plus, but this is now 150 cm cubed. So the concentration of the H plus ion we need to calculate. Okay, so let's do that. The H plus concentration, so concentration is moles divided by volume, so N over V, so that's 5 times 10 to the minus 3 divided by 0.15, and that comes out at 0.03 recurring, so 0.0333, okay, moles per decimeter cubed. So the pH is the minus log of that. I'm just going to move some of this. Oh, I don't know if I can do it. Oh no, I've destroyed that beaker. Sorry. Right, I'll just have to do it up here. So the pH is minus log of 0.0333, and it comes out at 1.48. That would be the pH of the solution formed. I don't know if you remember the other night I was showing you that grid that I'd made to help with revision purposes. One of the websites that I was linking to was called Chem Sheets, which has got that £12 subscription charge, but you would get access to hundreds and hundreds of questions like this, and all the answers there as well. So if you want to get good at questions like this, you need to practice, practice, practice. And there's not that many in textbooks, there's hundreds on Chem Sheets, so I would definitely recommend, you know, shelling out that £12. It's not a lot of money, I don't think. You get a lot of benefit from doing that. Okay. Right, final one. Calculate the pH of the solution formed when 250 cm cubed of 0.3 moles per decimeter cubed sulfuric acid is made up to 1000 cm cubed with water. Okay. So again, if you found the beaker sort of treatment helpful. So what have we got here? We've got 250 cm cubed of 0.3 moles per decimeter cubed H2SO4. 750 cm cubed obviously added to take it up to 1000. Okay. I'll just run through that again. So we're starting off with a beaker of 250 cm cubed of 0.3 mole per decimeter cubed sulfuric acid. 750 cm cubed of water is added, and so therefore you've got 1000 cm cubed. That's your total volume, isn't it? Okay, so the first thing I'm going to do is work out the moles of H plus. So the moles of H plus that we've got to start with is going to be 2, because it's di-basic or diprotic, 2 times concentration times volume, 2 times 0.3 times volume 0.25. I'll just put C and V on there so you know where they've come from. And the 2 is obviously because it's diprotic. and that comes out at, I'm just looking at my notes, 0.15. Okay, so there's 0.15 moles of H plus ions in that beaker. There will therefore also be 0.15 moles of H plus ions in that beaker. And the nice thing about this question is it's in 1000 cm cubed, so that is actually the concentration. So the H plus concentration, moles over volume, so it's 0.15 divided by 1, it's 1 decimeter cubed, so it's 0.15 moles per decimeter cubed, and therefore the pH is minus log 0.15, which is 0.82. Yeah, the default of the log button is base 10. Okay. Some textbooks you'll see a little subscripted 10 after log, but in a lot of textbooks they don't bother because it's the default base. Okay. So that's as far as I was going to go today, because we're at a nice sort of point in the topic where there's a sort of shift and we'd start looking at weak acids. Okay, so that's where we'll pick things up next week. In the meantime, definitely subscribe to ChemSheets, or have a look at my other videos on all of this. You're welcome, Laura. Thank you. You too. I hope that was all right. I hope that all made sense. You're welcome. Goodbye to you, clutter free. Right, I'm going now. See you later. Bye.